Hello everyone, welcome to the video. Today we are going to solve the problem permutations of a given string. In this problem, we are given a string and we have to return all the permutations of this string. We also have to return them in lexicographically sorted order. This problem is a bit intimidating for beginners because it requires a bit of structured thinking to break the problem down into smaller subproblems. It further uses recursion and dynamic programming. We are going to solve this problem today, but we won't directly jump to the solution, and instead we'll think through step by step and reach the solution. We discuss the questions of data structures and algorithms on this channel in simplest words with fundamental approach. If you are new to this channel, please subscribe. Let's start. To begin with, let us first note the key things down from the question. We are given a string S. We have to return all the permutations, and all the permutations should be lexicographically sorted. So for example, if we are given the string ABC, this is what our output would look like. Here all these are the permutations of ABC string and these are sorted in lexicographical order. So if we consider our solution as a black box, we are getting a string as an input and we have to return the list of string as an output. So what does our function signature look like? Our function signature would look something like this. Before moving to the solution, let us first visualize and make some observations. Here is the given string and here are the permutations. Now, how many permutations will be there for this string whose length is n? It will be n factorial. But now let's think of a case if there was a character which was duplicate here. Let's say instead of ABC it was AAB or AAC. Then would still the number of permutations be n factorial? No. We know that number of permutations will reduce in case duplicates are there. So our first observation is that we have to eliminate duplicates. Now we also need to return the results in lexicographically sorted order. So we can see here that first we only have the strings that start with the smallest character, which is A, ABC and ACB. Then we have the strings which start with the next big character, which is B, BAC and BCA. And then we have the string that start with the next big character, which is CAB and CBA. So what is happening here is that we are fixing the first character like A, then B and then C. And once we have fixed the first character, we are permuting the rest of the string like BC and CB here, then AC and CA here and so on. So this is our second observation, that we are going to first fix the first character and then we will permute rest of the string. How will we fix the first character? We will simply pick every character one by one in sorted order. For example, if the string ABC is given, we will first fix A, then permute BC, then we will fix B, then we will permute AC, then we will fix C, and then we will permute CA. So we will also get the output in lexicographic order. But what if the string given was BAC? Then how would we have done it? Then also it would be pretty simple. We will have to just first sort this string BAC into ABC and then we can do the same thing. If the question did not ask for had not asked for lexicographic order, then we could simply go with the BAC as well. We will first fix the character B as first character and permute rest, then we will fix A as the first character, then permute rest, and then we will fix C as the first character. But since the question asked for lexicographic order, we'll first sort it and then we will pick character one by one from left to right. This brings us to our third observation, that we may have to actually sort the string initially to get the lexicographic order. Now let's focus on the second part. We can now fix the first character. Now the second part is, how do we permute the rest of the string? So if we see this overall problem, we have broken it down into smaller problems. We are saying that okay, we will first fix the first character A, then give me the answers for all the remaining all the permutations of the remaining string BC. then we fix the first character as B, then give me the answer for all the permutations for remaining string, and similarly for C. If I have that, can I not simply compute the permutations of ABC by just appending the first character? Yes, I can. Now let's see. If the given string is BC and I am asked what are the all possible permutations of BC, I can simply see that yes, it's BC and CB. But what if it was very long string B, C, D, E, F? It would be difficult for me to figure out what all will be the permutations of that long string. But then again, let's think, isn't it the same problem that we started to solve? We are given a string and we have to return the list of strings which are the permutations of this string. Therefore, we can safely say that we have to use recursion here. And this brings us to our fourth observation, which is that we can break our original problem into smaller subproblems. How are we saying that these are smaller subproblems? These are smaller in terms of input size. For example, when our input was ABC, the length of the string was 3, while when our input is BC, the length of the string is 2. Therefore, if we are able to get the answers for smaller subproblems, we can use them to get the answer for our original problem. Therefore, we can see that we can use recursion here to solve this problem. Also, important thing to note here is that all the 4 observations that we made are very common and will be used in multiple problems, like elimination of duplicates, fixing first character and then permuting the rest of stuff, sorting the string or whatever input was given initially itself, and most common one would be recursion. In many of the problems, we will have to judge whether we can break our original problem into smaller subproblems. How do we judge that? Their input and output would be similar and the size of input will be smaller than the original size. And there, in such cases, we can use recursion. Let us now see the approach that we have so far. So far, we know that the permutations for the string ABC are nothing but the permutations when the first character is A plus the permutations when the first character is B plus the permutations when the first character is C. Now, how do we know what are the permutations when, let's say, the first character is A? In this case, we simply ask ourselves to get the permutations for this string. If somebody magically gives me answer to the remaining string, that is the permutations for the remaining string, can I get the permutations for this whole string? The answer is yes. I just need to append this character A to all the permutations of the remaining string, because first character is fixed. We were looking for the answers of the permutation of this string where the first character is A. So this is what is our current approach. We first figure out, we definitely have to iterate whenever we are given any string. And in every iteration, we will have one first character. For example, here in first iteration, we will have A as the first character. In second iteration, we'll have B as the first character. And in third iteration, we'll have C as the first character. Once we have the first character, we need to figure out what is the rest of the string. For example, here if A is the first character, rest of the string will be BC. Then we have to figure out what are the answers for the rest of the string. How will we figure out this? We know we'll have to make a recursive call because it's the same input output problem. So we'll figure out the answers for rest of the string. Then once we get all the answers, we'll append this first character to all the answers to get all the permutations where the first character is this one. And then we will add these two final results. We will maintain some final results which will include these. Then in second iteration, all the results with the first character as B will be added. Then in third iteration, all the results with first character as C will be added, and we'll finally return the final results. Do we see the problem here? Now, remember our first observation was to eliminate duplicates. Now let's see if, let's say, if the given string was AAB, then in second iteration, we will again have the first character as A after we had A in the first iteration. Therefore, we will have the duplicate results. And since we are returning list, the results will overall contain the duplicates. So how do we eliminate duplicates? The very common approach to eliminate duplicates is to not use list but use something that doesn't contain duplicates. What is the data structure that doesn't contain duplicates? It is set. So instead of returning list, we can return set. Then there is another problem. If we are returning set, that means we will now need a different function to be the recursive function. Why? Because our original function is to return list. So we cannot use that as the recursive function that we will recurse upon. Since we are now returning set, that means there will be some another function, let's say that we call a util function, that will basically return set given a string as input. So there will be a different function that will be used here in the recursive call. This is a very common approach that we can use often to eliminate duplicates, that instead of list we use set. We should also notice one more thing. Whenever we are using recursion, we should always check if we are calculating the output for the same input again and again. For example, if the string given here was ABCD, then we would first fix A and then we need to find answers for BCD. To find answers for BCD, we will first fix B and then we will find answers for CD and so on. Similarly, in another iteration, here we will first fix B and then we have to find answers for ACD. And to find answers for ACD, we will first fix A and then we have to find answers for CD. So for CD, we have to find the answers twice. It is clearly inefficient to calculate this 2 times. Also, this is only just 2 character long for now. But what if this was a bigger input? What if this input ranged to like 15 characters or 100 characters? Then it would be so inefficient. And also it is possible that if the input was large, there may be more than 2 branches where we have to calculate the answer for the same input. That same input is getting inputted in this function. So we need to eliminate this inefficiency. This is a very common problem that we will encounter in recursion. We want to solve for the problem P, but as we solve for its subproblems, we encounter duplicate subproblems like the problem P3 here. Here P3 needs to be calculated twice, which is inefficient. So how do we eliminate this inefficiency? We can say that whenever we first encounter the problem P3, we should just store the answer to P3 directly somewhere. And then whenever we come to the second time and encounter P3, we should, instead of calculating again for P3, we should just find the answer of P3 and return that. Now, how do we do that? What data structure suits us best to store this? That data structure should be fast in storing the result, and it should also be fast in retrieving the result back. What is such data structure? That data structure is map. What will be the input? Map is basically a pair of key and value, right? So what will be the data type of key? The data type of key will be the data type of whatever is your input. So input type could be string, input type could be integer, input type could be anything complex, even list of lists or anything. So the data type of this map would be whatever is your input type, and similarly the data type of value will be whatever is your output type. How will we use this map in our recursive call? It is simple that in our recursive function, now in addition to the input, we will also pass the map. Then before calculating for input, we will just first see if we have already calculated for it. That means we'll check in our map if the answer for this input already exists. If it exists, we return it directly from the map and we do not calculate. And if it does not exist, we write the whole logic of calculation. And then before returning the output or before returning the result for this input, we put that in the map so that if some time later again the call for this input comes, we don't have to calculate again, but we can directly return from here. This is the most common technique that we will use to solve the recursion problems. This technique is also called memoization, and this is basically dynamic programming, that we do not calculate the results twice for the same input, but we store the results somewhere and then we get those results whenever we need or we encounter the same input again. Let us now apply this to our original problem. This is our recursive function. It takes the input as string and returns the output as set of string. In addition to the input string, it will also take a map as input, as we discussed in the previous slide. Now, what will be the data types of this map? Its key will be of the type string, which is the input's data type, and its value will be of the type set of string, which is the output's data type. Now, how will our algorithm look like? We will have two functions. One is our original function that takes input as string and returns the input as list of string. And one will be our recursive function that takes input as string and map and returns the output as set of string. In our original function, we will first sort the string. We will declare this map that will be passed to our recursive function. Then we will call our recursive function with the original string as input and the map, which is empty, in step 2. We will get this in the form of set, but set is unordered. So we need to convert it into list. So we convert this set to list and then finally sort and return. Why do we sort? Because we need the results in lexicographic order. Now let's see how will our recursive function look like. Our recursive function takes the input as string and map. The first step is to check in map if this input has already been calculated. If it has been, we will directly return the result from the map without calculating further. Second step will be to check the terminating condition of recursion. If there is any function that is being called recursively, basically that function is calling itself, there has to be a terminating condition. And terminating condition will often be found in the smallest possible inputs. So here the smallest possible input will be when the string's length is just 1. Like we have the character B or C or A. We will fix first character and then we will calculate all the permutations where the first character is this. So how do we do that? We fix the first character, we get the rest string. Then we make the recursive call for the rest string and get the answers for that. Once we have got that, we just append the first character to all the answers. And then we add that to final results. Final results is something that we will maintain. So here we add the results where the first character is this. And in every iteration, we will add results where there is a different first character. So then once we have them, we put the result in the map. Why do we put the result in the map? So that whenever we encounter the same input again, we can directly return from the map. And once we have put that in the map, we return. What will be the time complexity of this approach? Here, there are total of n factorial permutations. And for every permutation, we have to traverse all characters of the string. So the time complexity will be big O of n into n factorial. Note that it is difficult to calculate the time complexity of a recursive call by the way we have been calculating time complexity in previous problems. So we have to find other ways, and here we could see that for every permutation we are traversing the length of the string. Therefore, the time complexity is big O of n into n factorial. If we have to check the space complexity, now since we are storing all the permutations in a set or in a list, so at a particular time, there will be order of n factorial space that will be consumed because of the storage of these results. So space complexity will also be this high. There is a variant of this problem where you don't have to return the results, but you just have to print all the permutations. In that variant, we will not need this space complexity, and we will use backtracking to solve this problem, which is discussed in a separate video. Let us now see the code walkthrough for the same algorithm that we just discussed. You can also find the link to this code in the description. So this is our original function. It takes the input as string s and returns the output as list of string. So first of all, we are sorting the string. However, we later realized that this step is not required and we can as well comment this statement. Why? Because we are anyway sorting the final results. So you can actually ignore this statement. So first of all, we declare the map stored results and note the data type of the map. The key is of type string, which is the input to our recursive function, and the value is of type set of string, which is the output of our recursive function. So we declare this empty map. Then we call our recursive function with the given input and this empty map. That recursive function should return us a set of string, which is basically the permutations for this string. Now this set will be unordered, so we convert that to list. Note that this is a very common way of converting a set to list. We then sort this list and we then return it. Now let's see how does our recursive function look like. Our recursive function takes the input string s and this map. This map is nothing but it stores the already computed values. So first of all, we check that if this solution has already been computed. If it has, we just return that computed solution. Then we declare a set of string final results that we will return as output, which is empty for now. Now we check in the terminating condition that if the length of the string is just 1, we declare a new set and add only that string in that set and we return it. Next, we have to calculate for the input if the length is greater than 1. So we have to iterate, and in every iteration we have to fix first character. Now to fix first character one by one, we first bring that character to the first position in the string. So here in the swapped string, we just bring the relevant character that we want to make the first character to the first position of the string. And once it is there, we know what is the first character. Similarly, now once we have the first character, we can calculate what is the relevant substring or the remaining substring, which is nothing but the string that starts from the index 1. Note the method substring here. How do we calculate the remaining substring? Then we have to calculate the answers for this substring. And how do we do that? We do that by using this recursive call to the same function, using this smaller input and our map. So we get the results here. But now we have to append the first character to all of these results. So we have created this method which does that. And now these are the results that should be part of our final results. So we add them to our final results. Now before returning these final results, we put them in the map. That is, for the input s, these were the final results. So that next time if somebody gives us the input s, we can directly return the final results. Now let's see the methods that we are using here. So this swap is nothing but it takes the character which is at position I and brings that to the first position. So for that, as we know string is immutable, we first convert this to the characters array, then we swap these characters and we then return a new string. Append first character basically takes a set of strings and appends the first character ch to all of these results. How do we do that? For that we will need to iterate over this set of strings. Now how do we iterate over a hash set? there is a method called iterator which returns the iterator object, iterator of string. Now this iterator object has two methods, next and has next. We make use of these two methods to compute the new final results and return them. So this is what our code looks like. Let us now summarize what all we did. First of all, we understood the problem with the help of an example. We visualized and made some observations. One of the observations was that we need to eliminate the duplicates. That prompted us to use set data structure instead of list. Second observation was that to calculate permutations for the whole string, we just need to fix each character one by one as the first character and then calculate the permutations beginning with that character. So for that, once we fix the first character, we have to permute the rest of the string. We realized that these are just smaller subproblems of the same problem we are trying to solve. They are smaller in terms of input size. That is, if the string length was 3 initially, in the subproblem the string length will become 2 and then 1. So we could infer that we have to use recursion. When we wrote the approach using recursion, we saw that there are duplicate calculations happening. So to avoid that, we tried to store the results in the map already. That technique is also called memoization. We then wrote the algorithm for it. In the algorithm, we had the two functions. One was original function that returns list, and one was the recursive function that was calling itself that returns set. And then we did a code walkthrough for the same algorithm. This is it for this video. If you like our content, please subscribe to our YouTube channel and our Telegram channel. We will meet again in the next video with some other problem. Thanks for watching.